last couple of times, we've been going over the basics of kinetics, stuff that I think everybody probably has seen at least somewhere before. Now we're going to go a little deeper, and at this point we start to touch on the most powerful parts, actually, of chemical kinetics. And so the other stuff is useful, especially as part of what we're doing now, but this is the part that's really useful for understanding what's going on, what controls the rate of a chemical reaction, and what's going on in a chemical reaction. In a lot of ways, the section we're entering now is like a transition from the macroscopic view of a chemical reaction, focused on the way that concentrations change with time, and moving down to the microscopic view of kinetics. That's kind of not really true. Both parts are really kind of a mix of microscopic and macroscopic. But in a sense it's true, because we're now going to start looking at more at the details of how a chemical reaction really goes. It turns out that a lot of chemical reactions that look fairly simple at first glance really involve a lot of complicated steps sort of underneath the hood, and that's what we're going to look at now. We're going to learn about something called elementary reactions as opposed to the general reactions we've been talking about so far. Then we'll talk about mechanisms. That's the title for this whole section. Mechanisms are collections of elementary reactions. And in the course of that, we'll do some examples that provide at least the beginnings of the way in which kinetics is connected to thermodynamics. There has to be a connection after all, right? All reactions go to equilibrium. If chemical kinetics can predict the course of the chemical reaction, then they must also predict the equilibrium point for the final chemical reaction. And thermodynamics does that too, independently by a totally different line of logic. And so there must be some close connection, in fact, between thermodynamics and chemical kinetics, and in fact there is. And in fact, we won't talk about these connections too much, because they get very deep and subtle and kind of beautiful, honestly, the theory does. But let me just say that these connections to thermodynamics are among the more powerful and beautiful of the theorems in non-equilibrium statistical mechanics that I mentioned a couple of lectures ago. All right, so what's an elementary reaction? Well, it's it's what it sounds like. It's a single-step reaction. It's a thing that doesn't have any other funny stuff going on. It's something that happens in one step. And so it's things like simple rearrangements of molecules, single bond-breaking events, and collisions between two molecules. Specifically, and we'll see this in more detail below, an elementary reaction is something where all of the reactants and products that appear in the reaction is all there is. There are no invisible species involved. A lot of chemical reactions, what's actually going on under the hood involves some other species that aren't even listed in the overall chemical reaction. For an elementary reaction, that isn't true. Everything is up front, and there's nothing buried or hidden. With more general overall chemical reaction, oftentimes there is stuff that's buried or hidden. All right, so here's some examples of elementary reactions. We take a single H2 molecule, the bond breaks, and we get two H atoms. That's a single bond breaking event. There's really no room anywhere for any intermediate or anything in between. This all happens at once, very rapidly in one step, or else it doesn't happen at all. Likewise, you can take those same two H atoms, cause them to collide, and they'll come together to form, or they can come together to form an H2 molecule. And again, there's not much more to say about that. There's nothing in between. There's no complicated stuff going on in here. The two collide, and if they manage to lose enough energy, then they stay together as a molecule at the end. And that's it. And likewise, you can have something like this. This is a much more complicated molecule now, but the change that's going to take place is simple. So you've got a chlorine here and a chlorine here trans to each other. The double bond in the middle normally doesn't rotate, but if enough energy comes along so that you can break one of those double bonds, leaving only a single bond, then you can get a rotation of one end relative to the other and get to the cis arrangement of the two chlorines. And that's a rearrangement step. And also there are no intermediates in that. It happens very quickly in a single step, or it doesn't happen at all. Here's another example of a collision between two species. An H atom collides with an O2 molecule, and as a result, the H atom basically pulls an oxygen off of the O2 and leaves their oxygen behind. Again, that's a collision between two molecules that results in this case, it results in both a bond breaking and the formation of a new bond all at once, but it all happens in one step, and so it's still an elementary reaction. Yeah. So the basic definition, or the most rigorous definition of an elementary reaction, is it has no intermediate species. We'll see a little bit better below what that means. And furthermore, the term or the name elementary suggests that you can use these very simple reactions to build up all of the other reactions that are more complicated, and that turns out to be true. We'll see how. In fact, the building up process is the business of making this thing that we call a mechanism for a reaction. Elementary reactions have something called molecularity, and the order of the rate law and the order of the reaction is equal to the molecularity. The molecularity just means how many molecules are involved. How many molecules on the product side are involved specifically. So in this case, I've got only one molecule involved. It breaks apart into two H's, but it doesn't matter what it breaks into. The molecularity, and therefore the order, is controlled entirely by the fact that there's only one reactant molecule here. Therefore, it's first order. One reactant, first order. Same for this rearrangement. It's a much more complicated molecule again, and it goes to the cis arrangement in this case of the, sorry, in this case I've got it going backwards. Got the cis arrangement on this side and the trans on that side. It goes to the trans arrangement, but it doesn't matter what the products are. There's only one molecule that's involved in the reactant side, and therefore it's also first order. If you've got two reactants in this H plus O2 reaction I wrote above, then it's second order. And that means it'll have a second order rate law, right? This is a first order rate law up here. This one will have a second order rate law down here. So H plus O2 goes to OH plus O. There are two products over here, but that doesn't matter. The order is determined entirely, and the molecularity is determined entirely by how many reactant molecules there are. And then in this case also, two H atoms come together to form an H2 molecule, and again, that's a second order reaction, a second order elementary reaction, in spite of the fact that there's only one product on this side. It is possible in principle. There are known examples where three molecules or atoms come together at once in a single ternary collision to form something on the other side. And that would be a third order reaction, would have a third order rate law. But such things are exceedingly rare. For all practical intents and purposes, it's really only first order and second order elementary reactions that you'll really ever see. If you see somebody saying, I've got a third order elementary reaction, you got to look hard at that. It isn't impossible, but it is very, very rare, very unusual. Yeah. All right, elementary reactions are also irreversible chemical reactions. That is, there's no backward reaction for them. Let's see what we mean by that. Let's suppose I consider these two elementary reactions, H2 breaking apart into two H atoms, or the opposite, the reverse case, the reverse reaction, two H atoms coming together to form an H2 molecule. There's nothing wrong with either of those. They're both elementary, and they're both separate. The fact that this one is the backwards reaction of this one doesn't mean they're the same reaction. They are separate reactions. Each of them has a rate constant in its rate law, and those rate constants are different. They even have different order, right? This is a first order reaction. This one's a second order reaction, right? Because only the product side matters. Sorry, only the reactant side matters, not the product side. And so The forward reaction and the backward reaction are different reactions, and they're both irreversible. You don't put a backwards arrow ever on an elementary reaction, because that backwards arrow is a different elementary reaction. Let's see, what else? Yes, each is irreversible. Each has its own rate constant. The rate constants are different, and the order are different. I said all those things, so we're good. Okay, what about those rate laws? Well, they are the rate laws we've already talked about. You can, and for an elementary reaction like these, you can write them down. For an overall reaction, the only way to know what the overall rate law is to do some experiments or else solve a mechanism, as we'll see a little bit later. But for an elementary reaction, we can write down the rate law right away. If it's a first-order reaction, the rate law is a first-order rate equation. If it's a second-order reaction, the rate law is a second-order rate equation. And if it's third order, again, very rare, then it's a third-order rate equation. So, for example, up here, the rate equation for this guy, or the rate law for this guy, would be R is equal to K1 times H2. The rate equation for, or the rate law for this guy would be K minus 1 times H squared, right? Because it's second order. It's got this 2 here becomes a square in the rate law. We'll see examples of this kind of thing in some detail when we talk about mechanisms down below. So anyway, if you have a second order case, then you get a second order rate law. If you have a first order case, then you get a first order rate law. Third order case, you get a third order rate law, always for elementary reactions, not for overall reactions. So for an elementary reaction, it's possible to write the rate law by inspection, just by looking at its order. But that's only true for elementary reactions, not true in general. All right, now we're ready to talk about what a mechanism is. An overall reaction occurs by a set of elementary reactions. In other words, if we consider an overall reaction like this one, so this is our sort of standard example, the water-forming reaction, 2 hydrogen molecules plus an oxygen molecule forms 2 water molecules. That's not an elementary reaction. How can we tell? Well, it can't be elementary, right? Because look what's going on. On this side, 2 hydrogen molecules are breaking their bonds, so that's 2 HH bonds being broken. Also, the bond is being broken on the oxygen. The double bond is being broken on the oxygen. And on the other side, 4 new bonds are being formed. That can't, although that bond breaking and formation can't be a single step. It has to be a multiple step process. And those multiple steps will be elementary steps, and the sum of them all, or the collection of them all, or the set of them all, is the mechanism by which this overall reaction, with all of its bond breaking and formation, takes place. So let's look at a possible mechanism. I want to give a disclaimer right away. This is my own mechanism, pretty much pulled out of the air. You can look it up online. Wikipedia even has a mechanism like this. And you'll see that it doesn't exactly match this mechanism. That's fine. I'm just using it as, it's a plausible mechanism, and I'm just using it as an example from which we can learn how to use such mechanisms to find out more about the chemical reaction. So let's look at the steps here. First of all, there's 4 different elementary reactions involved, 4 different steps in carrying out this overall reaction. The first step is just the H2, it's the one I wrote above, it's just the H2 molecule breaking spontaneously. So what we're saying is that you've got 2 H atoms that are bonded, and for some reason that bond actually breaks. How does that happen? Well, the bond's pretty strong, so this doesn't happen very often. It has to be something statistical, right? That this molecule collides with something, it somehow gets a whole lot of energy, a whole lot more energy than it normally would have, at room temperature at least. And then that causes the bond to break. And so it's going to be a rare event, but it's not a completely non-existent event, and that's good enough. Then what happens? Well, now you've got loose H atoms. They are very reactive, right? They want to be bonded together. They want to be bonded to something, but they're not bonded now. So the first thing they collide with, they're going to react with. And they can collide with another H2, but that doesn't do anything useful. What's useful is if they collide with an O2, because now this very reactive hydrogen atom can pull an oxygen off of the O2 molecule and leave behind another very reactive oxygen atom. Again, now this is running around very reactive. The first thing it collides with is also going to react with. It can react with another O2, but again, that doesn't do us any good. What does do us some good is if that O reacts or collides with an H2, because then it can pull an H atom off of the H2, form another OH, and another loose H atom. So from our original 2 loose H atoms, we've now produced some O atoms and some more H atoms. And now this OH, and also these OH radicals, right? These are not full molecules yet, right? These are radicals with unpaired electrons. And so these radicals can then collide with another H2 molecule, pull still another H atom off of that H2 molecule, finally form a full stable H2O molecule, plus leaving behind another reactive H atom. So you can see what happens once you've got a few of these H's and O's going. They'll start colliding around, and eventually you'll get some water molecules, and then once you get the water molecules, nothing more happens after that, right? Because the water is pretty stable. It's pretty hard to bust up a water molecule. And so everything eventually drains from H2 and O2, the other stable molecules, into the H2O molecules, but you create these weird, loose, free radical atoms in the meantime, and we'll say something about that. The presence of those things is extremely important, and it's the thing that separates an overall reaction from the elementary reactions. All right, so a few things to point out. As we've gone through, the elementary steps generate the overall reaction. Notice we're consuming H2. No new H2 is created. It's just only consumed, only destroyed. We're consuming O2. Again, no new O2 is ever created in the rest of it. We're producing H2O. Notice we're not destroying any H2O. So we're doing exactly what the overall, in at least a rough way, exactly what the overall reaction says, consuming H2 and O2, producing H2O. But by means of all these funny intermediates, these free radical high energy intermediates along the way. And so, again, this is what I mean by saying that the mechanism sort of shows what's going on in the microscopic scale, right? This overall reaction that we've been looking at since forever, probably, it's a very common reaction, isn't really a single thing. It's really made up of a whole bunch of smaller, simpler steps. And these aren't really, the true mechanism for this reaction is a lot more complicated than what I'm writing here. It can probably have hundreds of steps before you're done. A lot of chemical mechanisms do, even for relatively simple overall reactions like this. There's a whole lot of stuff that goes on. A lot of it's minor, a lot of it isn't very important. This probably does get sort of the major things that go on, and I guess it's worth pointing out that this is a type of chain reaction. In other words, you can see that at the end here you've created the water molecule, but you've also left behind another H, which can go back into the cycle up here. And so once you get this thing going, it can self-perpetuate, and that's why this reaction can be explosive. In fact, it produces enough heat to make this reaction much more likely. That produces a lot more H, which ultimately produces a lot more heat, which eventually gets, dangerous, or can be dangerous anyway. All right, so the 4 steps that we have here sort of tell us what's going on microscopically with the true reaction. Yes, they show what's going on with the action. They're showing how the bonds are broken, right? An H bond, two H bonds broken, two HH bonds broken, an OO bond broken, four water OH bonds formed. How does that happen? Well, it shows, right? Here's one of the H's being broken. Here's another one of the H's being broken. Here's the O2 bond being broken. Here's one of the OH bonds being broken here or formed. Here's another one being formed, and finally here is the last one being formed for the H2O. And so you can see that it's telling us exactly how all those bond forming and bond breaking events actually took place. All right, what else? Yeah, all these steps are irreversible, and notice each of them has its own rate constant. I put rate constant K1 here, K2 there, K3 there, and K4 there. And all those numbers are things we will have to know or get at least some idea of in order to analyze this mechanism and reach conclusions about the nature of the chemical reaction from the mechanism. Let's see, yes. I pointed this out already, but now let me emphasize it. There are three species that actually appear in the overall chemical reaction, right? This one, and this one. H2O2 and H2O, there they are. Those are, I'll call the majority species. But there's three other species that appear. The O, the H, and the OH, all these weird high energy ones, those are intermediate species. The fact that these are there, they exist, and yet they don't show up in the overall reaction is why this guy is not an elementary reaction. Its mechanism involves intermediate species that aren't formally part of the reaction at all. And you'll notice that when you look at the truly elementary reactions like this guy, for example, there aren't any, you can't break it down any further. There aren't any missing hidden species in this reaction, for example, or this one, or any of these. And so these are elementary, and this one is not. This one is not because it's composed of simpler elementary reactions. Yes, so these species, these intermediates, now not all intermediates are like this, but they often are. It's not an invariable rule, but it's a common thing. That intermediate species are high energy and reactive species. That means they're unstable. They tend to react almost immediately after they're made because the first thing they collide with after they're made, they react with. They rip atoms off of things, they collide with a wall and get deactivated. All kinds of things happen to them. They're just reactive enough so they want to react with whatever they touch next. That means they're short-lived. That means they're almost always in extremely low concentrations. And that makes them hard to detect. If you want to go finding out whether this mechanism is correct or not, one thing to do would be to get some experimental spectroscopic technique, like I suppose, and try and look for the presence of these guys, right, these high energy intermediates. But because they're present in such low concentrations, that's oftentimes hard to do. So it's very often the case that people, scientists, chemists will propose a mechanism like this one, and then years will go by and lots of research will go by before you can really verify whether the mechanism is true or not, because this mechanism makes predictions about the kinetics of this reaction, and we'll see how those predictions are made as we go along here. But those predictions are never enough to really prove that the mechanism is correct, because other mechanisms might make similar predictions, and that in fact often happens. And so the only really good way to settle whether such mechanisms are true or not is to start looking for these intermediates, start looking for these elementary reactions themselves, and that usually takes some really sophisticated experimental methods and stuff, and oftentimes it's very hard to do. All right. Yes, and that's what I just said. The presence of the intermediates is the reason why, formally the reason why this is not an elementary reaction. Okay, now that leads us to the last topic for this lecture, which is the business of actually using this mechanism up here to say something useful about what's going on with this chemical reaction. So we are going to use this mechanism as an example for writing rate equations, as I say here. In other words, we're going to take this mechanism, which is just a set of statements about what kinds of reactions take place, and we're going to write rate equations from those. Those rate equations are differential equations that can, in principle, at least be solved. Sometimes the sets of differential equations are complicated, and you have to solve them on a computer, but in principle they can be solved, and in fact there are lots of computer programs that are set up to do exactly that. And people do that kind of thing all the time. So the mechanism is going to give us not one rate equation. Up above we talked about first order rate equations, second order rate equations, but that was always just one equation at a time. Now we're going to get a whole set of them at once, and we have to solve them all at once or analyze them all at once in some way. Very often people can get a pretty good idea of what the behavior is, even for a pretty complicated set of rate equations, by looking at it qualitatively without actually going to the trouble and uncertainty to some extent of trying to simulate it on a computer. All right, so let's see how this is done. Here's our here's our mechanism, and there are 6 chemical species in that mechanism. The 6 we talked about, H2O2 and H2O, the 3 stable ones, and then also the 3 intermediates, HO and OH. There will be one rate equation for each of these chemical species. So for this mechanism, because it has 6 species, there'll be 6 rate equations, not one. Let's look at one of them. There's going to be a rate of change for the H2 concentration, right? So dH2 dt is going to be equal to what? Well, if you look at the mechanism, then this elementary reaction will cause the destruction of H2, right? Remember, it's irreversible, doesn't come back, doesn't go backwards. So the only thing that this can do is destroy H2, and there'll be other places where H2 is also changed, right? Here, H2 is also destroyed by this elementary reaction and also destroyed by this elementary reaction, and each one of those elementary reactions is going to make a contribution to the overall rate of change of the H2 concentration, and that's what I've written down here. Here's the rate of change for H2. There's a contribution from reaction 1. There's a minus sign in front of that contribution because H2 is a reactant. It's going to go away. The minus sign is telling us that we're losing H2. So there's always a minus sign when the species in question, when the species over here is a reactant. So the minus sign, and then because it's rate equation number, it's elementary reaction number 1, we write the rate equation for elementary reaction number 1. What is the rate equation for that? It's K1 times H2, right? That's the elementary reaction for reaction number 1. Notice when we do this, the elementary reactions never involve the products. They always only involve the reactants. And so even though we may be interested later in the way in which H is changing, and H is a product, the elementary reaction for this elementary reaction, the rate equation for this elementary reaction will always only involve the reactants themselves. So it's K1 times H2, and that's exactly what we have here. That's the contribution from reaction 1. Likewise from reaction, so H2 doesn't appear in reaction 2, so there's no term from reaction 2 here. But there is from reaction 3 because H2 is in reaction 3. And what's the rate equation for reaction 3 here? Well, the rate equation is going to be K2 times O times H2, right? It's a second order elementary reaction due to a collision. And so it's O times H2, and that's exactly what we have here with a minus sign because the H2 is a reactant again. Finally, for reaction number 4, H2 appears there also. And again, it's a reactant, and so there's going to be a minus sign. And then we need the rate law for reaction 4, which is going to be K4 times OH times H2. And overall, then, we've now written down one rate equation out of the 6 that we can write down for this mechanism. which has three contributions, one contribution from each of the elementary reactions where the species in question appears. All right, let's do that for the next case and see what we get. Let me get rid of some of this garbage. Makes it hard to see. All right. So let's see. I'm saying the same things here that I think I've already said. One contribution from each elementary reaction that contains H2. Each contribution is equal to the rate law for that elementary reaction. There are plus signs for reaction for which H2 is a reactant, or sorry, minus signs for when it's a reactant. And in this case, it's always a reactant, so there are three minus signs there. There will be plus signs when H2 is a product. Now, in this particular mechanism, H2 is never a product, and so there are no plus signs in this particular case, but there would be if it were a product. We'll see that happened in some of the other cases. All right, let's do the next case. Let's write the rate equation for the disappearance or appearance, the rate of change of the intermediate H. The fact that it's an intermediate doesn't matter. It's still got a rate equation. Now, in this case, here's our mechanism again. Let's look where H appears. It's here, it's there, and it's there. It appears in all four of our elementary reactions. But notice that it's a product in three of them, and it's a reactant in one of them. So we're going to skip pluses and minus signs. But the other thing that's new, and the reason that I didn't write it all out at once, is because notice that two H atoms are made in this first step. That means we have to double the rate law out here. So this is the rate law as normally written. We've doubled it because we're producing two H's every time in this first step. All right, so there's a plus sign because it's a product here. There's a 2 because it's got this 2 in front of it, a stoichiometric coefficient of 2. And then there's the rate law itself for reaction number 1, and that's the term for reaction number 1. Let's look at the rest of the reactions. Here's the same term as above. I just rewrote this down here now with the rest of the terms. Here's the term from reaction 2. Here's the one from reaction 3. Here it is from reaction 4. Let's look at those, see if they make sense. So for reaction 2 here, we have that the H is a reactant, so there's a minus sign. The rate constant is K2, there it is. There's an H and an O2, so H times O2 is a second order step. And so that's the rate law for number 2. And is there anything else? No, I think that's it. Then for number 3, same thing. But now H is a product, so there's a plus sign. And now even though H is on this side, we still, when we're writing the rate laws, we still only use reactants. So it's K3 times O times H2. O and H2 are the two reactants in this case. And then finally for K4, H is again a product, but again the rate law is only going to involve the reactants. So it's K4 times OH times H2. If we go and do that with the others, which we can do, then you get the following. I won't go through these all in detail now, but I encourage people to go through them on your own, because if you can go through them and get all these right, if you can start with this without looking at the answers and get all these guys right, then you probably pretty well understand what's going on. If you can't get them right, then you probably need more practice. I'll give you opportunity for that in the homeworks and stuff. All right, so here they are. Here are the other rate equations. Notice that for O2, it only appears in one place. There it is. That's the only place. That's reaction 2, and so there's a contribution from reaction 2 here, but there's no other contributions from the other reactions. Let's see, for H2O also, the only place it appears is in reaction 4, and it's a product. So notice there's a plus sign there, K4, and then the rate law, OH times H2 for the contribution from reaction 4. Some of these others, OH here appears bing, bing, and bing in 3 different places, so it's got 3 different contributions. And for O, it appears in just 2 places, so it's only got 2 contributions, and so on. It's not terribly hard. Once you get the knack of it, it's not terribly hard to do these things. This is, in fact, a fairly complicated mechanism as things go in this class, at least. We'll see some mechanisms that are, yeah, a little bit more complicated than this when we talk about enzyme kinetics in the next chapter. But this is probably the most complicated one we're going to look at in this chapter. And that is it for today.